Hi everyone, my name is Claire Tomlin and I'm a professor of electrical engineering and computer sciences at Berkeley. And this is the 29th module in a series that we're recording for the course EECS 221A, which is linear system theory. I'm going to have a brief module just to present something called the spectral mapping theorem in this one. And it follows on from our previous module where we presented the Jordan form of a matrix. So I'm going to start by just recapping a Jordan form. So if we had a matrix, and I'm going to write down a possible Jordan form J for that matrix. This is an example where we have two repeated eigenvalues, one at lambda 1 and one at lambda 2. And the matrix is not diagonalizable, but it can be put into Jordan form. And this is just an example again. So it's an example where we have one Jordan block of size 3 associated to the eigenvalue at lambda 1. So there's the Jordan block of size 3, and those are 1s, and everything below the diagonal is 0. One Jordan block of size 2, so lambda 1, 1. Okay, again, that's a 0. And then I have 3 repeated eigenvalues at lambda 2, and there's a Jordan block of size 2 and a Jordan block of size 1, lambda 2. Okay, so there's 4 Jordan blocks related to this system. The minimal polynomial, which we defined as psi hat A of S, so associated to, actually it's not A, it's J, associated to this matrix J. We can just read off immediately from the Jordan form. So the largest Jordan block associated to the eigenvalue at lambda 1 is 3, and the largest Jordan block associated to the eigenvalue at lambda 2 is 2. Okay, so that gives us the minimum polynomial. Of course, the characteristic polynomial we can, of course, read off right away, and that's just going to be s minus lambda 1 to the 5th, because of the 5 eigenvalues at lambda 1, and s minus lambda 2 to the 3rd, because of the 3 eigenvalues at lambda 2. Okay, so we also see from this, as we talked about, from our knowledge of the similarity transform that brought us into the Jordan form from a general matrix A with this structure, with this eigenspace structure, is that there's 4 eigenvectors associated to this matrix. So there's 4 eigenvectors, 1 for each Jordan block. So 2 eigenvectors associated to lambda 1 and 2 associated to lambda 2. It's an 8-dimensional system, so that means there's 4 generalized eigenvectors. Okay, so brief recap of the Jordan form. The function of, now suppose we have a function, a matrix, a function of a matrix, so some function f. Let's suppose that function f is analytic on the spectrum of J. Then we can calculate that function of the matrix. And as we presented last day, the function f of J can be represented in terms of an operation on the Jordan form, and it's given as follows. So that is also, in this case, in this example, it's an 8 by 8 matrix. So f of J is also an 8 by 8 matrix. And it's a matrix, it's a block diagonal matrix. So associated to, we have similar blocks associated to the corresponding eigenvalues. So there's my blocks for lambda 1, blocks for lambda 2. Here's the one block associated to that eigenvalue at lambda 2. Okay, and then as we presented last day, the form of that function is f of lambda 1 on the diagonals, f of lambda 1. And then on the superdiagonals, the immediate superdiagonal, we have f prime of lambda 1. So it's the derivative of f with respect to its argument evaluated at lambda 1, f prime of lambda 1. And in the upper right-hand corner, we have f double primed of lambda 1 over 2 factorial. Okay, then everything else here is 0. So similarly now, we'll have, again, f of lambda 1 on the diagonals, f of lambda 1, and f primed of lambda 1 on the superdiagonal, 0 here. F of lambda 2, f of lambda 2, f prime evaluated at lambda 2, 0, and then just f of lambda 2. Everything else is 0, so these are zeros. Okay, so it's an upper triangular matrix in general, and so the eigenvalues of this matrix f of j are just the diagonal entries. And so we see immediately in this Jordan form and the function of the Jordan form that the eigenvalues of f of j are just f of lambda I, where lambda I are the eigenvalues of the matrix j. And so this is true in general for Jordan forms, and of course in the special case a diagonal form. And this leads us to the statement of the spectral mapping theorem. So the spectral mapping theorem is just the statement of this fact. Spectral mapping theorem. Okay, so remember the spectrum is the set of eigenvalues of a matrix. So and we denote sigma the spectrum. So sigma of f of j, the eigenvalues of this function f of the matrix, is equal to f of sigma of j. Okay, so it's the set f of sigma of j. So it's the set f of lambda I, where I ranges from 1 up to however many eigenvalues we have. And actually, we use the terminology sigma, a different sigma previously for that. So basically, you take all of the eigenvalues of j and you evaluate f of those eigenvalues, and that gives you the eigenvalues of f of j. Okay, so we've done a recap of the Jordan form of a matrix, and then we've done a recap of the functional form of that matrix, so f of j. So we have a general form. Basically, once we're given the Jordan form now and we're given the function that we want to calculate of that matrix, we can write down the function of the matrix by inspection. And then from that general form, we get out the spectral mapping theorem, which states that the eigenvalues of f of j are the set of eigenvalues, that function evaluated on the eigenvalues of the matrix j. Okay, so now we're in the future modules, we're now going to use this. Remember the point about this Jordan form is in general it gives us an easier way of computing functions of a matrix. And the main function that we've been interested in is the function e to the at, the matrix exponential, where a represents the system dynamic matrix, the square matrix which represents the system dynamics. So now we can think about how we might transform a to Jordan form and then compute e to the jt using a formulation like this. Okay, thank you very much.